Okay, I think we can start. Can people online hear me?
Yes.
Yes, perfect. Okay, great. So the second chapter is Ising model. Has anyone heard of or studied Ising model before? It's about modeling ferromagnetic behavior. And what is a ferromagnetic behavior? Anyone? Yes, the spins of the individual atoms in a material align and create a larger magnetic dipole behavior. And this can be used in a lot of different areas, and it's especially in the data storage. It's used to be. I don't know if anyone in this room here is old enough to recognize these kind of patterns. You have these kind of cassettes in the past. I speak like a 70-year-old, but yeah, I mean, I personally used for a lot of years these kind of Walkman things before the more advanced technology came. And here you can see that there is a very tiny magnetic tape on this kind of cassette player. And what is used here is that they kind of force a certain kind of magnetic registry on a certain is a one-dimensional tape that you kind of register spins there. So kind of you apply a very strong magnetic field, and then since it's the temperature is too cold for this material to readjust its spins, it will kind of remain frozen. That's why you find these permanent magnets in the nature. They once get magnetized, and then the temperature is now low, and they cannot really change their field because there is not enough thermal energy for their spins to fluctuate and thermalize. So this is used, of course, in a lot of things than that, but importantly, we want to use, again, as I told you before, every chapter is presenting a particular problem, but the idea behind every chapter is we are actually showing a certain method using this kind of example chapter. So here, the important thing we are going to tell you is the Monte Carlo algorithm. So Monte Carlo algorithm is going to, instead of simulating the system dynamics directly, in the previous chapter, molecular dynamics, what were our approach? We were taking all the particles of the system, right? And then we are evolving the system according to differential equations with tiny steps. With every step, you're solving the equation, what is supposed to happen in the near future, what is supposed to happen again, what is supposed to happen again, and then we are evolving, propagating the system in time like that as a whole. Monte Carlo algorithm takes another approach. We are kind of proposing a change in the system first, and we are accepting or denying this change with a certain probability. And if it's a physical system, this probability will be proportional to the exponentially decaying with the potential energy of the change state. Which means that, has anyone have an idea about this formula? It's the Boltzmann formula, right? What is it? In thermodynamics, we have a probability of occupying a state for a particle with energy EI is given by this formula, is proportional. If you ignore the Z first, this first term, one divided by Z, it's just there for normalization. This is probability is proportional to E2 minus EI divided by KBT. KBT is the thermal energy that represents the amount of fluctuations, energy fluctuations in a material. And the probability of occupying a state with energy EI is given by this formula. So if a state has an energy that is very high, my particle will be less likely to spend its time there. If there is a state with lower energy, my system or my particle will tend to stay there more often than the higher energy states. And here, Z is just the sum of all these terms for all the states, so that all the probabilities of different states will add up to 1. Anything that is probabilistic, the sum of all the probabilities should add up to 1, so it's normalized. How do we apply this on a system of on a lattice of spins here? So the Ising model is simplifying this problem of magnetic spins of atoms into a two-dimensional simple model. In reality, a spin of an atom can be in any direction, right? Dipole moment of a magnetic dipole moment of an atom can be directed in any direction, in 2D or even 3D. But here we only consider them one-dimensional. So it's either directing up or down. So we are simplifying the problem first. And we assume that they interact with a very simple equation. The energy of this system is, let's see. How do people erase here? Very, very nice. Except that you have to hold this as well. So the interaction energy that I assume this system have is that the let's say or sigma I, we can say. So sigma I is the spin of each of its neighbors. So for each cell, we are considering it's interacting with only 4 of its neighbors. Okay, and we are considering this. So now we are going to consider only this cell, and we think about what energy states would this cell have if it's +1 or -1 spin. And the formula is like this. And then sigma I, this is sum over j, sigma j over its neighbors. So here, what is the, so I have 3 neighbors that is pointing up and 1 neighbor that is pointing down. What is the sum? This cancels this, the sum is 2, right? This is 2, and I have an external magnetic field also. That in that case, I think -0.1, -0.5. So what happens is that, let me see. If it's -1, no, it is, I don't remember. Let's check. Yeah, my external magnetic field of -0.1. What happens is that if this spin were to have a down spin, this would have -1.1 overall energy, otherwise +1.5. According to this energy states, I can then have what is the probability of this particular cell pointing upwards is P plus, I can notify this, and this can be, sorry, let's go to here. So this can be calculated using this formula. So what I can do is that because I only have 2 states here, E minus and E plus, because I only have 2 possible options, it can either point up and down, and my partition function, which takes care of the normalization, will take the form of this, right? Exponential minus beta here is 1 over kBt. So there is no confusion. These are the same kind of formula. And what happens is that since pointing up for this particle is more favorable, it has a lot more neighbors in the direction, +1 direction, the energy of the particle pointing up is lower, which means that the particle likes to stay in that, is going to be more likely to be assigned to that state when iterated. Is this clear? Any questions? So each state have a probability, and they are exponentially proportional to the energy of the state. And for this particular particle, the physical intuition is that this particle has three neighbors that are up, right? And think about these as magnets. You have three neighbor magnetic dipoles that are pointing in one direction. This magnetic field compensates. I mean, this is kind of outcompensated by this, let's say, and we have two more neighbors in physical interpretation. We have neighbors that are pointing in the +1 direction spin. I am more likely to align with them, although there is thermal fluctuations. And these kind of probability distributions depend strongly on the temperature, which means that if the temperature is very high, which means what is the temperature? Temperature is associated with the average kinetic energy in the material, right? If the temperature is very high, it means that there is plenty of energy fluctuating available in the environment. So a lot of collisions, very messed environment, iterating so much, which means that the probability of a single particle going against the mainstream is going to be a lot higher if the temperature is high. If the temperature is low, that's why we have a comparison here. This is for the ratio of probabilities at a relatively low temperature. If I can recall again from the figure. So this is when the temperature is 5 kBT. Sorry, the kBT is 5. I mean, compared to the interaction strength J of the spins. So when it is 5, you can see that the temperature is 5. The probabilities are still relatively close to each other. And we show a comparison. What happens if the temperature were to 1? You see that in that case, the particle is almost certainly will go to the state that is aligning upwards. So how does this work? If the temperature is high, the system behaves more randomly, right? If the temperature is very low, the particles will have a lot higher probability to align with their neighbors. This is the physical interpretation of this formula and the model. Is this clear? Do you have a question? No? Okay. You agree that it's clear? Okay. It's good. So I will then next demonstrate how it works in real simulation. So in some chapters where it's possible to represent the system with an animation that is running in real time, we have on GitHub this kind of codes that you can have a look. It might give you an idea. Of course, I once again underline the fact that these lectures are independent from the homeworks, and these are just to show you and like make you able to play with the system, get an intuition how it's going to. We are not expecting you to provide the same code that is presented in the GitHub, but I will use this the code to just, if I can move it here. Yeah. Can people online also see this?
Yes.
Yes, perfect. So this is a simulation that we have two parameters here. The first parameter is the temperature. Temperature is again associated with the kinetic energy of average kinetic energy of the particle in the environment, in the state of the matter. And then if I increase the temperature, what will happen is that you see that the spins will go a lot more random, right? And as I decrease the temperature, they tend to align more with each other, which is natural because the probability, according to the Monte Carlo algorithm, of occupying a state that is aligning because it's lower energy to align with your neighbors, it's a lot more favorable when the temperature is lower. And you see that the things are aligning with each other quite well, even if the temperature is still relatively high. And of course, you can play a lot with that decreased temperature. You will see immediately as you decrease the temperature, there are domains that are formed. And of course, this is also dependent on the external magnetic field. Right now, they form really slowly, but if I increase the magnetic field in one direction, you see most of them are going to have the plus. If I go in the other direction, you see that the minus spins are growing. And of course, once let's say once it's fully magnetized in one direction, You see, this is exactly what's going on a magnetic tape. This part is registered with a certain magnetic field, and the temperature is not high enough that it's going to be changed itself. So you can, with no cost of energy, you can store information for practically infinite amount of time. Of course, you can take this as an example of magnetic susceptibility. It doesn't have to be ferromagnetic, right? There are lots of material that is paramagnetic, which means that they are way above the critical temperature. What happens is that around the material, it's quite random, but what happens is that whenever you apply a magnetic field, more spins inside the material align. So average magnetization of the material is increasing in one direction, proportional to the external magnetic field that I apply. All this system works with this simple formula, and I kind of choose a random element at a time in the lattice and iterate its state according to Monte Carlo algorithm. And all this kind of real life behavior can be very easily, like, think about how simple is this model. I mean, we are talking about the interaction between two dipoles, right? Magnetic dipoles, which is very complicated, especially if they are close. The analytical solution is very, very complicated. It will make you cry. But we are just saying that if it's +1, we have the energy +1. If they're opposite, we have the energy -1. I mean, we have a term J, but we kind of assume that is 1, and we kind of just manipulate the external field. We have a huge assumption here. We totally disregard all the individual formulas, but we are still able to obtain very interesting real life behavior using this formula. It's a very strong model. Any questions about this? Of course, you can try to, for example, initialize the system differently, try to play with it once you have made the model. For example, you can make lines of different magnetization and try to see in which condition they break into each other, what happens. And there are lots of different examples. You can check what happens in 1D. You can check what happens in 3D. All of them are significantly different from each other for Ising model. Is this clear? Yeah. Okay. Now I will continue. So let's go on. So I showed you in the animation what happens, but if I repeat, if the temperature is very low, even if I start randomly, they will quickly align with each other, and you will see formation of domains, magnetic domains, because some particles get near each other and try to group up in one direction, others maybe other direction. Sometimes it doesn't have to be always like this. If you run it a few times, maybe you will see that sometimes they will all align in one certain direction. Of course, this is a finite dimensional system. It doesn't perfectly reflect what happens if the material is super large. However, if the temperature is at a critical temperature, which I will explain in the next slide, what is criticality, they will try to align, and this alignment time scale, length scale, is going to increase over time continuously, but they will never fully magnetize. And if the temperature is above the critical temperature, you will see that the random behavior of the individual spins are going to be like this. And this is kind of a behavior of a paramagnetic material. So the spins are normally random unless you apply a strong external magnetic field. And then they might align in one direction more than the other. But this means that their internal interactions between their neighbors are weak compared to the thermal energy. What is one of the most famous ferromagnetic materials? Is there any Italians here? Giovanni, yes. What is ferri in Italian? Yes. Yeah. So that's not obvious, but is it ferri or
iron, right?
Fe? Yeah. I mean, iron is the most common example of a ferromagnetic material. The reason is that its interaction with its neighbors. I mean, if people were to use English at the time, maybe that's, I mean, I don't know the history of ferromagnetism, how it was discovered, but I think it was discovered in Latin times. That's why it's meant. They are named.
Probably goes back really to.
Oh, yeah.
Because it's not something very difficult to. If you have a magnetic substance and you take that piece of iron with it goes with you.
Yeah. Yeah, it should have been observed long ago, before the English was the kind of language of science. So that's why iron is the most common. And the reason is that the interaction between individual spins that are neighbors are so strong that at room temperatures, they can't really just fluctuate freely from their, like independently from their environment. They kind of align and preserve their magnetic value.
Would there be any benefit including the more elements?
Yes, and there are exercises. I don't know if there might be.
Yes, it will work. We'll change the threshold, but there is benefit to the signal. Basic model, just a second. Basic model in one dimension was solved very quickly. In two dimension was solved very much later. Three dimension is thought not to be solvable now. If you have also the diagonal element, you have much more difficult, so you can do less than numerical difficulty.
There is no difference in the qualitative results.
There are differences in qualitative results between dimensions. So, for example, in one dimension, you don't have.
But I think the critical temperature would change if you include.
It will change quantitatively.
Qualitatively, it will be the same, but the critical temperature you observe, if you instead of 4 neighbors, if you were to include 8 neighbors, it will change. But of course, these are the experiments, numerical experiments you can do yourself. It's very interesting to see what happens if I include 8 neighbors instead of 4. What happens if I include solid boundaries? What happens if I include different kind of, for example, particles? You can think of a lattice with 2 atoms, right? One is like you have 4 immediate neighbors of one kind and then 4 diagonal neighbors of another kind. So kind of a different lattice structures, and they are maybe different, interacting with different J's. And you might even observe like multiple critical points in the system. I am guessing, I am not stating that you will observe. I don't know what will happen, but yeah, it might happen. And in terms of numerical numbers, what will happen is that here, what I'm representing M is the average magnetization of the lattice. So what in average the magnetization of the material, right? And if the temperature is very small, what happens is that they all align. Sometimes they all align in one direction together. Sometimes they all align in other directions. Sometimes they create these kind of domains. They kind of group up, but like kind of saturate at another level. But immediately the full alignment between different between neighbors occur. You see that this is a qualitatively different behavior at the critical temperature, and these are simulated like 10 to 5 steps. It's a very long time step that we are simulating the system, and it's still not reaching to an equilibrium. This fluctuation and alignment getting polarized in one direction is going on and on over time. But the time it takes to reach the full alignment or an equilibrium is very, very long at critical temperature. And on the other hand, if the temperature is higher than the critical temperature, what happens is that the average magnetization is just fluctuating around 0, because there is enough thermal energy to just fluctuate the spins around, and it's never really aligning between, like, individuals cannot really form clusters of a certain polarization. Is this clear? You have no questions? No. And the really key way to find the critical temperature is that what is happening to the average fluctuation in long term? If I wait long enough, what happens? And here you can see that this is after a very long number of time steps. If I want to be accurate, check here. This is after 1,000,000 steps in the simulation, and average further over 10 times of different realizations. So I run the simulation 10 times 1,000,000 steps and then take the average. What happens to the magnetization? And you can see that after a very long time, if the temperature is higher than this critical number, they don't really get to align well with each other, although there's an increasing. But this increase is really how sharp is this curve is really about how long I have simulated it. If I simulated it 100,000 steps, it will be a lot less sharp. It will be something like this. If I simulated it for 10,000 steps, it will be a lot less sharp. And if I had time of, I don't know, if I had a better computer or I had time for running this for days and wait for it patient, I will see a sharper transition and sharper transition. As I run the simulation for longer time, I observe that this transition becomes sharper and sharper. You see that this is really a critical behavior. At this particular temperature, system is behaving in a totally different way. Is this clear? So that is why we call this system critical. So there exists one particular temperature when the system behavior is changing significantly, especially in the long term. Is this clear? It is what? Yes. I am not sure if I understand. Path. Previous.
Is it just that it's like they will align to certain values, or do they align because they are close to each other?
I think they align because they are close to each other, and it's favorable energetically that they align. And this is, by the way, this figure here is representing the system with absolutely no external magnetic field. This is a system with no external magnetic field. If you were to apply an external magnetic field, the system behavior can change. And of course, you won't really observe for example, if I had even a very tiny external magnetic field in the +1 direction, probably all of these -1 cases would disappear. Of course, this is random. What is happening is that it can go either direction. It can go, I mean, in the beginning, it's quite random, initialized, and then they are randomly aligning with each other. At some point, one spin is getting stronger than the other, and it's kind of occupying the lattice. But it really, this sign doesn't really, this is actually like a local kind of behavior, and it could go in each direction.
Could I ask a question?
Yes.
In this figure on the left, we can see that the magnetization for low temperatures can become pretty small, like on average.
What do you mean very small? On the right, you mean?
No, on the left, in some instances.
In some instances, yes. I will repeat the question. Yeah.
Yeah, but in the next picture, pretty much all the dots for low temperatures, the magnetization is pretty large.
Okay. Yeah. Yeah. If I understand correctly, you are referring to this one. All of them are very high, right?
Yeah.
Yeah. Okay. So I will rephrase the question. Question was that someone from online asked, is that in this picture, we see that sometimes they are fully magnetizing and sometimes they are kind of saturating at a certain value and staying there. However, in this plot, we are kind of observing that all of them are kind of almost fully saturating when the temperature is low. The difference between the two plots is that this one is run for 100,000 steps, and this one is run for 1,000,000 steps and repeated 10 times. And if you run the system for a lot longer time, what will happen is that, and I take the average, and the difference, and you still have the cases where the magnetization is kind of the domains form in opposite direction and it's lower. You see that these individual points here, it still happens, but it happens in a way that, and actually that is kind of the reason I cannot go further back. Those cases, the number of exceptions would increase, and these kind of exceptions you see on the left edge of the simulation would increase if I were to decrease the temperature further, because the immediate cooling down to a very low temperature result in really localization of the magnetization, and it will prevent them from really like this randomness is not enough in that case even to align all of them in one direction, and these exceptions will increase a lot if I have this further lower temperatures. Does that answer the question?
Yes.
Yeah.
Thank you.
Okay. Yeah. Yeah, exactly. I mean, the point is that the verifying the same behavior as the temperature is lower is gonna require me to, this is just obtaining this figure is not easy. Try to obtain it yourself and try to make it this sharp. Is you will have to simulate very long and average over many realizations, because the critical temperature, at critical temperatures things take time, and these fluctuations take infinite amount of time to kind of reach the ground state of the system. So you really have to simulate for a very long time. That is one drawback of this model. Any other questions? There is another kind of behavior that I didn't mention here, but in some cases this J can be negative, which means that the spins of individual neighboring atoms tend to align in opposite directions. That is energetically more favorable. This depends on the lattice distance between the particles, because the magnetic field of a dipole is like this, right? It really depends if you are how close to it. So very close, they are in this direction, the other way, they are the other direction. Now, it's a three-dimensional structure of fields, so it's not really trivial, but sometimes they tend to align in the opposite direction. What happens in that case is that if the temperature is very low, it's really like a chessboard structure that is forming. Every neighbor is different from another. It's a lot more difficult to analyze, because there you don't directly see the formation of domains. You kind of see this chessboard structure, which ends up in average zero magnetization still, even if they are fully aligned. And its response to external magnetic field is also different than the ferromagnetic version of the Ising model. But you can just, the only thing you have to change in the equation that in the animation code, for example, is setting J to -1 instead of +1. And then everything else is the same. You can try to observe what's going on if the system was ferromagnetic. Okay? Is this clear also? Does it confuse people? No. Okay, great. And of course, we can use this kind of a model to analyze. It doesn't have to be particular for atomic spins. You can use this model to analyze different kind of systems. For example, here we have an exercise where you can actually demonstrate critical Casimir forces using Ising model. What is critical Casimir forces? Has anyone heard of Casimir forces? Quantum electrodynamic Casimir forces. The source of the force is that if you have a two metal plate that are very close to each other in space there are electromagnetic fluctuations, and they can occur in every single wavelength all around us, right? And we are talking about very small length scales here, by the way. And what happens is that if there are two metal particles very close to each other, they confine the amount of wavelengths that can exist between them. So the quantum electromagnetic fluctuations are confined a lot in the area between them. There is a lot more fluctuation outside than inside. It's an electromagnetic effect, and they kind of attract each other due to the pressure, electromagnetic pressure that is happening from the outside due to this effect of the metal is annihilating the electric field at its surface. Is kind of acting as a boundary condition for these waves and confining them. And this results in a very large force, especially if the particles are very close to each other. This is a big problem. This is a problem we never feel in the microscopic world, but in microscopic world, it's a big problem because like two metal plates that are a few tens of nanometer size, if they get close to each other, they just stick. And it's very difficult to separate them from each other. And critical Casimir forces are related to these forces, but here what is confined is the fluctuations, critical fluctuations of the solvent. A critical mixture is a mixture of two liquids that are dissolved within each other above a certain temperature, and they are kind of demixing under a certain temperature. So think about a certain kind of a common example is water lutein. So it's a kind of an oil that is kind of dissolving within water. So they look totally homogeneous. But as you go down to a certain temperature, which is 34 degrees something, what happens is that they demix. And very close to the critical temperature, there are large critical fluctuations occur. You can kind of simulate this also, kind of model this system also using Ising model. What you have to do is that you kind of assume the same Ising model. The spins fluctuate up and down. Instead of spins, you can think of the values here is being occupied by one liquid or another, right? And then we put particles here that are solid. So we don't actually iterate them. They are a certain kind of material. And if, for example, they are hydrophilic, you can assume that they are like water. If they're hydrophobic, you can assume like they are oil. So you don't change their state. It's mathematically the same thing as you were doing the Ising model. And then what happens is that what you can do is that you can put them close to each other and then try to calculate the average potential energy of the whole system as a function of distance between the particles. Because what will happen is that if, for example, the particles have the same affinity, let's say both are hydrophilic, which like water, so you put them as a block of water, kind of block of +1, and then you will observe that the region between them will be mostly occupied by blue. And you here see that if this is yellow, this region will be mostly occupied by yellow. So this kind of, when they have the same affinity or the opposite affinity, this will kind of inverse the behavior of the system. So what you can do here is that you simulate the system. The only difference is that you kind of take this square block of particles. You don't iterate them. They are constant. And you just run the system for a long time, calculate the average potential energy, put them a little bit closer, calculate the average potential energy of the system for after a long time, closer long time. You can then obtain potential energy, average potential energy of the system as a function of distance between the particles, right? Which means that if you have a potential as a function of distance, you can calculate the force by taking the derivative of the potentials. You kind of numerically calculate with Ising model the forces of critical Casimir forces. This is, of course, not related to direct calculations of critical demixing and phase fluctuations in the liquid, but it kind of gives you a model that qualitatively simulate the same kind of behavior. So it can also be used in other systems. Is this clear? Is there any other questions? Any other question from the audience? Let's see, there is one. I am going there. Bro, can anyone else not hear anything? Can you hear me? Is it an old one? Ah, okay. Good. If you don't have any questions, yeah, we can. Yes. You can say if you want.
I mean, there are things. First of all, I will announce the groups tomorrow because I wait all today. If you want to suggest or to ask to be put in a group together, you can send me basically until midnight tonight. But if you don't, I will put in a random group, and then it's final. Okay. There are still 36 people that have not asked for anything, which is fine. I mean, if you don't care where you end up, fine for me. But I just wanted to remind you that. Was this understood by everyone? I want to be sure that everyone understood because maybe someone was not in the class and so on. Okay, so you have until midnight. CET. And tomorrow I will announce the groups, so then you will know what are your groups. You should immediately get in contact and start thinking about what project you would like to do. Look at all the chapters of the book so that you get ideas about what could be done. Look at the challenges and problems we have at the end of the chapter.
They don't have them.
We don't have them? What do you mean we don't have them? We have problems at the end of it.
No.
We removed them from here.
We removed them from here.
Okay, we have them in the
We
real
didn't.
book. Okay.
Wait until no, don't wait.
Don't wait. Anyway, from the topics of the book, you should be able to get a feeling for what you want to do. But look at all of it. Don't look only at the first elements, okay?
But there are also further readings in each at the end of each chapter. You can
Yeah.
also have a look at them. Also, not all exercises are included in homeworks. There are lots of exercises in the book still that are also demonstrated, but not given as a homework.
Yeah, but in the published version of the book, which is not available yet, will be available after the end of the course in practice, probably at the end of December. There are also challenges and problems at the end, which are more advanced. But you don't really need them. You need to know that you have a whole scope of possibilities, and you should look into that. Okay, start thinking about that and in the mail I send tomorrow, I will also tell you who is your tutor. So you know already who is your tutor. You can get in contact as soon as possible. I will suggest so that you can discuss your idea, and you will also know who is your review group. Also, in that case, I will suggest you get in contact as soon as possible. Okay. Any doubts about this? Online, I don't know if anyone.
Any questions?
If anything is unclear, we can clarify now. That's one thing. Second thing, the homeworks. It looks like everyone understood what to do, so I don't see any problem because no one wrote to me saying that it was unclear what they had to do. But is there anything that is unclear about either the homeworks or how they are structured, how the correction will be done?
There is a question. You can, if you can speak, you can ask Christian.
Okay. Well,
If it's a particular question about a certain homework,
We can do that.
you can email me. But if it's a general question about the evaluation or the structure of booking,
no, it's specific.
if it's specific, yeah, you can email me or
Or we can ask
find
immediately
me.
after, right?
yeah, or I can take it immediately after also. Now, okay,
right.
you can just wait in the room. Okay.
Okay, so just to repeat it. So you saw today, you got the message at 8 a.m. Their schedule, so they will go out exactly at 8 a.m. on Fridays. That's for registering for the homework correction next week. I think it was clear because it looks like clear on the doodle. The good thing is that no homework was oversubscribed, which means that you can basically choose what you want. So it seems all fine. And it looks like there is a good spread across students between different chapters. So I don't see any problem at all, unless you tell me that there is any problem. Okay, and the correction will be done either online. So we will have the same Zoom link. You can join via Zoom, or you can come to the class, which is the one written on Canvas. So it can be in person or online. It's up to you. We don't really mind. But you should be there at the time you have subscribed. It might be that we are a bit delayed and you have to wait a bit longer. It might be that you have to wait. So bring something to read or to do during the time you have to wait, because sometimes there might be small delays. Okay, so if you subscribe between 10 and 10:45, it might end up that you are corrected at 11. It's unlikely from what I see, but it's possible. Okay, so put a bit of margin. If you want to come earlier than your time, you can do that too. If you have an extra space, we will take you. Okay, is this all clear? I think it's pretty And I will close the doodle. You can change a bit the doodle. You know that you can change the homework or the time slot. Fine for us. I don't really mind. But we will close it on Thursday morning. So Thursday morning is finalized. That's what it is. Okay. Until then, if you feel like you want to change homework because you decide that you really don't like the one you're trying to do, you can switch it. No problem. I don't advise that you do that. I advise you that you first read them all and then choose the one you like best so that you don't waste time. But you're free to change, no problem. And yeah, then I don't know. Is there anything unclear or anything that you would like to discuss about the organization of the course of the homeworks? Okay, last thing, as you will have noticed already, this material is new. It's the first year we are using this material and we are really planning to use it for many years. This is fortunate and unfortunate for you because it means that there will be some mistakes like the one you already found. It's very good for you, for us actually, and for the future students that will come after you if you can report all the things that are unclear, even things that are not just wrong, but just unclear. It's like a sentence that you interpret in 2 different ways and it's not clear. We can still change it. So just let us know. Write us an email, or even better, write it as an issue on GitHub so that we can keep track of all of that. Any problem that you find, just let us know. And of course, the good part for you is that we will be a bit more lenient on the grading, since we know that there are some of these problems. In the future years, there will be less. We will be more strict. Okay. Any question? Okay. Good. So we can be here for a few more minutes in case someone has specific questions about the homeworks or something you want to discuss.
Yeah.